Let's talk about what embeddings are. First, a vocabulary in this context is just a list of all unique words in the dataset. For the English vocabulary, it is every English word in the dictionary. Let's form an example sentence. Each word is actually represented as a vector, encoding information on its meaning. These vectors are embeddings for our model input. First, let's import our important classes. So PyTorch, NN, and Math. Then our first class to code is the input embedding. So we will first do embedding. The NN module, this is the base class for all neural network modules in PyTorch. There's two methods for each PyTorch module to define. The init method, which is where we will define layers and parameters for our model, and the forward method, which defines the forward pass for our network. This is where we will specify how our data will pass through each neural network layer that we define in the init. Okay, so let's go forth. In our init class, again, this is where we define the layers and parameters for our model. We pass in dimension and we pass in the vocab size. We want to instantiate those. And then we have an embedding, which is just a vector of that size. For our forward pass, we just return the embedding with it a little normalized by dimension of the embedding. Great. Now let's talk about positional encodings. As we know from the previous part, embeddings are a vector representation of vocabulary. But how will transformers know where the word is in relation to the sentence, paragraph, or page? After all, using the same words, we can achieve totally opposite meanings. The cat sat on the mat versus the mat sat on the cat. And this is where positional encoding comes in. Transformers use a brilliant mathematical trick involving sine and cosine to encode position as a vector. Sine and cosine waves will create unique patterns for each position, but makes it also easier to extrapolate what the future or past looks like due to its oscillating end behavior. The formula looks like so, where pos is the position, I is the dimension of the positional encoding we are calculating, and D model is the embedding size. For even indices of the positional encoding, we use sine. For odd indices, 2i plus 1, we use cosine. This encoding is then added to the word embedding, so each word carries both its meaning and its position in a single vector. The beauty of this approach is that it allows the model to easily compute relative positions, meaning it can understand that word 5 is closer to word 3 than a word 20. Moreover, it can handle sequences of varying lengths and positions it hasn't even seen before because of the reliable behavior. Our next class to write is the positional encoding. For our init function, we want to specify the dimension of the embedding that gets passed through and also the max length of the positional encoding, because that determines how big the matrix of the positional encoding will be. Of course, we also want to set a maximum length of the sequences that the model can handle. We don't want to process 2 billion tokens. Init function is great so far. And then our positional encoding matrix, which has a dimension of max length and the dimension of the embeddings. And then we will have a position and div term. So the position is the numerator in our formula, and the div term is our denominator in our formula. A range makes a list from 0 to max length incrementing by 1, so like 0, 1, 2, 3, 4, and then max length, if it's like 500, will go to 0, 1, 2, 3, 4, 500. And then unsqueeze will add a dimension to our matrix. We're adding the dimension at position 1, so this is position 0, and now we have a additional dimension at the second position. So now we have a 2D vector. And then with our div term right here, we want to basically multiply them together and then sign them for our formula, or if it's on the odd terms, we want to cosine them. So now we have our positional encoding matrix all figured out. We add another dimension at the first point, and then we transpose the first and second dimension, which then switches the dimensions to max length 1 and then D model. We add this to our buffer so that we could use it in our forward method. And my thing just crashed. And we are back. So now for our forward method, essentially we add our input embedding with our positional matrix, and it has dimensions of max length, batch size, and then dimension of the model. And then of course we specify the index of it for the max length to be whatever index we have currently for our forward layer, and then we apply the dropout. Layer normalization, as opposed to batch normalization, serves to normalize each data point individually. Let's say we have a batch of these 3 colored items. To normalize an input, we would find their individual means and standard deviations and apply the norm formula on the input x. One additional thing we want the model to do is to scale and shift the normalized features by gamma and beta respectively. Both of these parameters are learned by the model over training. The next class to write is the layer normalization. Let's start writing it. So for our init, we don't want the D model. Usually the PyTorch implementation of layer normalization has dimension because you want to normalize over a dimension. But here we'll do a trick and we don't need the dimension. We can just multiply by 1, which is why we have this 1 dimension here, by the way. Copilot calls it alpha and bias, but in my formula here, alpha is gamma and bias is beta. 2 different names for it, doesn't matter what you call it, but to stay consistent with my video animation, I will rename it to gamma and beta. For our forward layer, we want to calculate the means and standard deviations for each batch, and then apply this formula to normalize x. The keep dimension is here so that the mean doesn't condense into just this one number, right? The mean is kept out through the whole dimension, so then we can actually be able to use beta and gamma to scale and shift the end number. This picture is from the paper Attention is All You Need. The last neural step of the encoder and decoder block is the blue feed forward layer. It is just a neural network with this formula right here. The input x gets passed through one layer of parametric weights and biases, and then that output is ReLU'd to an output layer, where it is then multiplied and added by a different set of parameters that we will train soon. Of course, we will drop some of the neurons so the model does not overfit during training. This is called dropout. Now let's move on to the feed forward block. Let's check if this is all correct. So yeah, we want the dimension of the embeddings that are being passed through. And we also want a dimension of the feed forward layer. You can also call this MLP dimension because this might also be referred to as the multi-layer perceptron, the MLP portion of the transformer. And then we have our dropout. Let's initialize it to 0.1 by default. And the feed forward block is essentially we pass in an X and then we put it through one layer of weights and biases, so one layer, and then we take the ReLU of it, which is just taking the max of 0 and the output, and then we just have another layer of doing the exact same thing. So we just create 2 layers of D model and then MLP dimension, and then we create another layer. And then for our forward, I guess this is one way to do it, but we can just simplify it into one line. Okay, we're going to use torch ReLU. I don't know where the F is coming from. We calculate layer 1's output first, and then we ReLU it. We calculate the output of layer 1, and then we ReLU it, and then this output is then dropped out and then applied to the second layer. Next is the multi-head attention, the first and most important step of the encoder and decoder block. First, we have an input matrix. We can think of this matrix as 3 words encoded with their position with a dimension of 3. Then we make QKV matrices, which are exact copies of our input matrix. We multiply them to their respective learnable weight matrices to get Q prime, K prime, and V prime. Here's where the attention comes in. First, let's write some formulas. Think of each column being a vector for one head of attention. In this case, because each matrix has 3 columns, there are 3 heads of attention for each matrix. The specific attention head is calculated by the formula on the right, and we do so for all 3 attention heads. For clarity, dk in the denominator of the left formula means the dimension on the vectors, which in this case is 3-dimensional. Nice! We have calculated head 1, head 2, and head 3. So we concatenate all the heads into one matrix. Let's represent this with H. The last step is to multiply it to the output projection matrix, which blends the attention of all the heads of the matrix into one. This results in a clean multi-head attention matrix that represents each word and its attention towards every other word in the input. Awesome. Now let's code the multi-head attention. So class head attention block. The D model makes sense. Then we have the number of heads. I like to rename this as heads. Then we instantiate the variables. Head dimension is the dimension divided by the heads. Remember how we have 3 heads here? The dimension of the heads are basically split into 3. So now it's like one of these dimensions are the head, and then there's 3 of these head dimensions. So essentially all it's saying is there's 3 heads if there's 3 rows. So that's head dimension. And then if we need to make sure that the number of heads is not 0, great. After that, we want to instantiate our weight matrices. WQ. We want to have each weight matrix be 2-dimensional with the head dimension. Because if you remember here, when we multiply by the weight matrices, we want to multiply by the embedding dimensions. The output matrix as well, which is also dimension versus dimension, and then drop out. Our forward. So let's check QKV mask. That's great. In our forward, we're going to first multiply QKV by their weight matrices, WQ, WK, WV. So let's do that. So Q prime would then equal prime would equal that, and then that. After this step, we split all of them into their respective heads. So let's just write a function to do that. Self.split. Cool. And then let's just make a note to ourselves to write a function that splits the heads. This actually does seem right. Essentially, what we're doing with split heads is we're getting the dimensions of X, which is batch size, sequence length, and dimension. And then you can recall this. It's from the positional encoding. So that's the dimensions of X. And then we are restructuring the matrix into 4-dimensional. We're adding this dimension heads, and we're turning these heads into head dimension and heads. If you multiply these two together, heads and head dimension, you get D model, which is the original dimension. We're splitting this 3rd dimension into the respective amount of heads that we want to put multi-head attention on. And then we transpose 2 and 1. So we transpose the sequence length and self heads. Sequence length and heads gets transposed because we want the head dimension to be related to the sentences. So the heads can actually put attention on both the sentence and the actual words. So that's split heads. Let's write our attention. Let's have attention. For our actual attention formula, so now we're doing this process of calculating the attention. We take in the Q prime, K prime, and V prime, the mask if there is a mask, and then the dropout. I guess I'll explain the masking right now. Masking, we want different attention heads to attend to different tokens. So we have these padded tokens in the matrices Q, K, and V. Some of them are 0 and some of them are not 0. And if we want to make sure to attend to a certain token, we make sure the mask is not 0. And then if the mask is 0, we make sure to make it a really small number so it never actually gets attended to. For our attention, let's just specify what DK is. DK is just the dimension here. Q prime dot size and -1 is just this. Remember that -1 means the last index. So that's what DK is. We want to calculate their attention scores. And remember, here's the formula. Basically, we have the square root DK here, and then we multiply Q prime and K prime, and we, of course, transpose the K prime. So that's this term right here. If the mask is not none, then we call the masked fill function in torch. We just do what I basically said. The masking sets all the padded tokens to -infinity so that they are not attended to. So then different attention heads can really attend to different tokens. And then we softmax. I don't know why it's saying F. So torch.softmax. We softmax this. And then if the dropout is none, which means the dropout exists, we drop out the attention scores and then multiply it to V prime. And then we also output our attention scores as well. We are calculating all of this and introducing a mask at this stage. So when we softmax, anything that doesn't want to get attended to becomes 0 when we softmax it. Next, we want to combine the heads. We use the contiguous method to really ensure that the tensor is contiguous in memory, which is necessary for the view method to work. So we switch the head and sequence length again. Remember how it was this. Now we switch 1 and 2. So now it's batch size, sequence length, heads, and the head dimension. And then we want to multiply the heads and head dimension together to get our old dimension again. And that's why this contiguous view is important. So then we can view the self.dimension into its correct readability. So that's combine heads, which is this step right here. We just combine the heads. And then our final step is to multiply it with the output projection matrix. And then that's our multi-head attention. So let's do all that. So we have split the heads and we want to calculate the attention. Just call our attention function. Then we combine the heads and then we multiply it by the output projection matrix. That's our attention. One last thing to really take note of is we have talked about multi-head attention. We've talked about feed forward, but how do we put them together into the add and norm step, right? We have the layer normalization step, which is the norm part. But how do we get the output of multi-head attention or feed forward into the add and norm, and also the input of the multi-head attention and feed forward to the add and norm, right? Because we want to add and norm both of those to get an output. So we will create a new class called big block or connection that connects the add and norm step with the feed forward layer or add and norm step with the multi-head attention, so that the input will be fed to add and norm and the output of the main neural step will be fed to the add and norm as well to create our desired output. So we're going to have this class that abstracts a whole big block right here. There's a big block here as well, big block here, and big block here. And we're just going to create a class that abstracts all of that. All right, now let's code this big block. We need to take in the input and then feed it to our sublayer. Could be feed forward, could be multi-head attention. And take that output and input, normalize it, and then add it to the input. Let's do that. And these are actually officially called residual connections, especially this. These are called residual connections. So let's code that up. We declare our norm and dropout for our init, and then for our forward layer, we take x, norm it, take the sublayer, take the output of it, and then we apply dropout to it, add it to the original x. Now we can put everything together and create the encoder and decoder class for our transformer. Each encoder class involves one multi-head attention add norm, which is the residual connection class, and a feed forward and add a norm. Decoder has the masked full multi-head attention, which I'll explain about the mask part, and then multi-head attention and then feed forward. Now let's finish up coding the transformer. One thing I forgot to mention, by the way, is the encoder and decoder both run n times in a loop, big N. Code our encoder block. For our encoder block, we have self-attention and a feed-forward layer. Again, self-attention means QKV is all from the input matrix, which is different from here. I'll explain later. Self-attention, and then feed-forward. Perfect. And then we need to make the residual connections for both blocks. We do a module list. And then for our forward layer, we create residual connections for the self-attention block and X, the input. And we create another residual connection with our new X, because X now represents the output of the self-attention block after this line. When we pass in X, it is the output to feed forward here. And then we pass in X to the add a norm step. And then we also pass in the output to the feed forward into this residual connection class. So now our X represents here the output of our encoder. That's actually only one encoder iteration though. We do need to make another encoder class to just run it n times and make sure that it passes for all the iterations n-1 and below, it passes it to itself. And then on the very last iteration, it passes its Q and K to the multi-head attention of the decoder. Class encoder. I like to call it blocks instead of layers, because feed forward has 3 layers, but you would call the feed forward layer or layers one block itself. So essentially we run the block n times. So blocks n encoder blocks. We're just going to pass in the encoder block n times. Now for our decoder block, it is essentially the same thing as our encoder block, except we're going to put what's called a cross head attention. So, it even auto completes that for me. First step is self-attention, and then it goes to multi-head attention, which is crossed with the encoder, and then our feed forward block. Yep, there's 3 of them now. Forward. Wait, we need encoder. So these are both tensors, X and encoder output. And then we have a mask for cross attention, and we have a mask for the self attention, which is the source mask. So first step, again, is to create a residual connection representing this block for the self attention. We pass in X, and then we pass in the self attention and the source mask. And then second step is, again, a residual connection with now the cross attention block. And instead of X and X, it's encoder output. For our last step, it's just a simple feed forward again, and then we have our final output of the decoder block returned. Let's make sure to call it n times. Actually, it kind of bothers me that source mask should go first, just because cursor tab is amazing. Holy. Because since source comes first and then the cross attention, I just want to organize it so that it looks like that. So that's our encoder and decoder. Now we can put most of it together. Wait. I'm forgetting one thing. So once we have the output to the decoder, we just need to put it through a linear layer and then softmax it. This is called the projection layer. So let's code that up really quickly because it's pretty simple. And then we can put all parts of the transformer together. Class projection layer. Okay, so this works actually, but think of D model as the input to linear, and then the vocab size is the output, because we want to basically map the dimension of the output of the decoder, which is D model, and we need to map it so that it covers the whole vocabulary, and then we can softmax to get the output probabilities of every word that could possibly be next in the sentence. So you can think of this as input and think of this as output for the projection layer. So we create a linear layer that takes in that and then outputs into the vocab size. You can also think of it as a 2D matrix, and then we apply the softmax to the lineared X, and that represents this part. It was batch size, sequence length, and then demodel, but now it's batch size, sequence length, vocab size. So now we can code our transformer. We pass in an encoder, and we pass in a decoder. We pass in the projection layer. We pass in the source embedding, the target embedding, and then, we're forgetting the positional embeddings. Source, positional, encoding, targets. That's everything we need. And then for our forward layer, we're just putting all the variables together. And since we already wrote the functions, we just let the functions do their thing and then return the final output projection. So we have our source sequence, which is just our source embedding with the source sequence. And then we have our target sequence. And then we positional encode it. So we pass in source encoding and target encoding to our positional encoding functions to get the new encoding that encodes position as well. And then we have our encoder output and our decoder output, which takes in the encoder output. And then we have our output from the projection layer. Awesome. So that's our transformer class. Let's now build a function to just call the transformers, to basically initiate the embeddings and everything and call the transformer function, transformer class. Okay, so we take in a vocab size, a target vocab size, sequence length, target sequence length, demodel, and number of heads, and dropout. Oh, we need to specify the num layers. Hello, this is Post Kyle speaking. I wrote num layers, but actually now that I realize it might be confusing to say num layers. I mean to say the dimension of the middle output layer for the feed forward block. So it would make more sense to just say DFF, which is also what the attention is all you need paper refers to that number as. There's 4 times more nodes in the feed forward block as compared to the input and the final output. Later I write all this code, just change num layers ff to dff, then you get your right code. I haven't written that code yet in the video, so no spoilers. Have fun. So now we've specified that. We put our first the source embedding and then our target embedding. Then we want to code their position. After that, we create our encoder blocks. For loop for n times, create a multi-head attention, feed forward, and then pass it into our encoder. block, append it to our encoder blocks. And so then we have a list of n encoder blocks in our encoder blocks list. And then we pass it to our encoder function, which again, encoder class, which just runs all n blocks. Great. And then we do the same for the decoder. Decoder blocks, the append. And then we have a projection layer, and then we make our transformer with all of that. We return the transformer, and that builds our transformer, and I think we are ready to start training with data. Okay, so I forgot to mention one thing. We want to initialize the weights of the transformer. So Xavier uniform basically puts it into a uniform distribution for the parameters, so then it's easier to get to convergence when we train.
Awesome. That's now our model done. Let's go to train our model now. Train.py. Let's import the important libraries. So first, we need to build a tokenizer. Every vocabulary needs a dictionary, a mapping from a word to a key/ID. That's what the tokenizer does. The tokenizer assigns each word in the vocabulary a number that can fetch the embedding for that word. So we're going to first tokenize the languages by the words. Let's build our tokenizer. We want our tokenizer to take in the config, dataset, and language. Let's specify the tokenizer path and import the necessary libraries. Remind ourselves to create this function. The token, if the path does not exist, meaning the tokenizer does not exist yet, we will need to build it. From the ground up, we specify the unknown token. We want to separate each word by the white space. So we instantiate the pre-tokenizer as the white space, and then start our trainer, which takes in the unknown token, the padding token, the start of sentence token, and the end of sentence token. And min frequency 2 means any word in the vocabulary that happens at least twice gets added to the vocabulary. Then we train it on every sentence that we have in our dataset that we get from HuggingFace. Oh, and that being said, here is the dataset that we get from HuggingFace. I'm going to use the Helsinki NLP Opus 100 dataset from HuggingFace. From AF to EN, we have a sentence here, and then its English translation. So that's what the data looks like. We train it with our tokenizer trainer, and then we save it on our file path when it's built. Otherwise, if the tokenizer already exists, then we just take the tokenizer from the file path, and now we have our tokenizer. Awesome. Next, let's make our dataset from our HuggingFace model. Not HuggingFace model, HuggingFace data. So import the necessary libraries. So we take in a dataset, a source tokenizer, a target tokenizer, languages for both, and then the sequence length, which could be max length. Let's instantiate those variables. And then we also want to do the tokens. Wow, it knows me. And then the padding token as well. Perfect. So this is the length function, returns the length of the dataset. And then get item, we make a pair. The pair is these two translations are the pair that we were talking about. So the source text is the one in the source language. Here, this is the translation class, which is why we typed this. And then the source language is the one that we pass in, which is in this case AF, and then target language is EN, but we could change it to wherever we want. Great, encoding and decoding. This transforms the text into tokens, essentially. Then we want to add the sauce and EOS and padding tokens. Encoding non-padding tokens. Okay, the reason why we have a -1 instead of -2 is we add both the starting and ending for the padding tokens. But then for the decoder, since everything is shifted to the right one, we don't actually need to do it at the end. We only need to do it for the label at the front. Great. Now for our encoder input, we essentially want to create a list with the start of sequence token, then we put our sequence, and then our end of sequence token, and then our padding tokens. Actually, a better way to do this is torch.cat. Perfect. It knows me. So for our encoder input, we want to concatenate
all 4 of these: the start of sequence, the actual sequence, end of sequence, and then padding token, but torch.cat instead of the plus. And then we can specify the dimension 0, which we can't specify with the plus. Wait, let's just delete this. Same for decoder, except we only add the start token. So we don't add at the end. We add the start token, then the sequence, and then the padding, which is why, again, there's a -1 here. We don't add to the end. Then our label. So our label is our decoder tokens, and then the end of sequence token, and then our padding tokens again. Make sure size tensors are all max length. And then we want to return dictionary. So encoder input is encoder input, decoder input is decoder input, and then the mask, the label, and the text. The decoder mask is actually going to be different. And the causal mask. So we're going to put a causal mask there. Wait, how did it know that I wanted to type a causal mask? That's insane. Okay, so the dimension of this is 1 max length. This is 1 max length and 1 max length. Now we need to write our causal mask.
All right, time to explain what a causal mask is. For our encoder, every word is attended to every word in the sentence. We do not want that for the decoder. For a decoder, we want to predict the next word for every part of the sentence. This means we start with the first word and calculate the attention on itself and all the words that have passed, which is none for now. Then, for our second word, we calculate attention for itself and every word previous, which includes the first word. And we do this for each word. With this attention only backwards, that's how we train the model to try and predict the word that comes after each word in the sentence, which is why we want to mask the attention past the word that we are attending to negative infinity. For the first word or the first row of the attention matrix, we mask every word's attention past the first index, same for the second, and so on. PyTorch has a method called tryu, which does this, and we specify that we mask along the diagonal. So, the causal mask, we create our mask. The function to do this mask is tryu along a diagonal. So we have our torch matrix along the diagonal. We make this a type torch int, and then boom. Now this is our causal mask. Now every word is going to be attended only to words that have appeared before it. Before preparing the dataset for training, we need to set up the config. So let's do that. So let's import our necessary libraries. Cool, batch size is right. So we want 20 epochs. That's a good learning rate. So this is the learning rate. Max length of an input sequence. This is demodel your embedding dimension. And then the source and target language, which for us will be AF and EN. Because if we look here, AF to EN for HuggingFace data that we're using. And then we specify the name of the folder that we want to store our weights in, and the base name for each model that we train. Let's store our Tokenizer file here too. Preload, none. Usually it's none or latest. You can actually do latest and then code that in. Here is where we store our experiments, which is just the encapsulation of all of our model trainings. And then let's write functions to get the weight files. So get weights. Actually, in our config, we're actually going to need to specify the dataset that we use. So let's just do that. Dataset name. Let's just make sure that that's the right. Yep. And then now we can load our model folder with our data source, dataset. And then another function to find the latest weights file for our weights folder. Model file name. We want to get everything that matches this regex weights files. And then if it doesn't exist, we return none. Then we sort them. Then we return the latest weights that we find. Now we have everything to go back to train our model. So let's first get the dataset. Get dataset. Pass in a config. Our dataset raw, and we just call load dataset with the dataset name
and then the language source to language target, and that's great. We only want to take the training data from HuggingFace. And then let's build our tokenizers. Then we're going to actually split the training data into the training and validation, keeping 90% of the data with training. So let's keep 90% the data for training and 10% for validation. Train size. And then train dataset. We need to import random split. Now we create the bilingual dataset that we coded in datasets, if you remember. So the bilingual dataset here. Oh, that's perfect. It read my mind. We need to find the maximum length, and then we just iterate through the dataset. Dataset raw. We need to encode it first. Source IDs, target IDs. So we encode each source and target language into tokens and then count how long they are. So this would be 1, this would be 2, and that's essentially what we've done. We want to load the data. We want to create data loaders for the training and validation. So train loader, and then the val loader, boom. The shuffle equal true means that the data will be shuffled before being loaded into the data loader, just truly random. And then we need to import that. Boom. And then we return our loaders and tokenizers. That's our data set. Now we can get our model. No, it was build transformer, right? Yeah, it was build transformer. It was build transformer. Put in the config sequence length, config d model, and then we don't mention any of these. Those get specified to their defaults, and then we return the model. Now we need to import the build transformer. That's great. Oh yeah. We should import that too. All right, let's train our model now. Def train model. Let's first define our device. If you are using a GPU, we want to use the GPU to train the model. Otherwise, we would use the MPS and then the CPU. But I definitely do not recommend the CPU. Or torch dot. Then we're just going to print using this device. Then we'll print more information about the device. And I actually copy pasted this print part. This is basically the code for printing what device will appear, and then information to go with that device. So now let's just make sure the weights folder exists. Otherwise we create it, and then we can really get started with actual training. So let's just make sure path config. It's not experiment name, it's dataset name. Config. And let me just make sure that's how it's specified in the config. Yeah, this is how we specify it right here. So that's perfect. That's the model folder. Then we make, if it exists, it's okay. If it's parent, it's okay. Then we call our get dataset function, which returns us 4. So then we get our dataset and our model from the functions above. I forgot to do the device. Device equal torch.device. So let's write our optimizer now. No, we don't need to use betas. We're using the Atom optimizer with our model parameters, specify the learning rate and epsilon. Oh, we need a tensor board. So tensor board. The tensor board is essentially how we log and debug our model training. You can think of it as just more print statements. Now we can start training. Initial epoch equals 0, global step equals 0. And then if we want to preload the model that we already have, if we do, which in this case, the way I set it up for our preload, we load the latest epoch of the model that we trained. So model file name, we want to call our functions. Latest else get weights, great. Then we need to import those. If the model file name exists, then we print that we're preloading our model, and then we define our state, and then load our model into the model state dictionary, load it with the optimizer as well, and then we want to set our initial epoch and global step to the epoch that we are currently at in our state and the global step we are currently at. Else, we just print that nothing has been preloaded, and then we just start from scratch. Now let's write our loss function, which we do need label smoothing. And then we can actually start training for our epochs. So for epoch, we start with our initial epoch, and then we go to our maximum num epochs, which is in our config. Let me check. Yes, right here, which is 20 in our case. So let's empty the cache first, and then we train the model. And then we want to iterate for each batch that we have in our batch iterator. So we split our loaded training data into batches using TQDM, and then TQDM actually tracks, it's like a progress bar, and it tracks how much we've trained. It's like a live progress bar. It's really nice from TQDM. So for every batch in our batch iterator, we have our encoder input equal batch encoder input.toDevice. That actually works. Oh no, it's frozen. And I have to restart VS Code. Oh, that's tough. That's tough. Reopen. All right, we're back. Batch encoder input to device. We do that for the decoder input and also the masks for both the encoder and decoder. Then we run the tensors through the encoder, decoder, and the projection layer. Basically our whole transformer process. Encoder output. And then we encode our model. Decoder output, model.decode, and then projection. I'll note down the dimensions of each part of the batch. So we have batch size, sequence length here in our input. Same for decoder input. We have our batch size, and then we have the sequence length of each batch size. And then our mask is a batch size 1 sequence length. And then our decoder mask has, instead of that 1, becomes sequence length because we want to predict every single word that appears. This is batch sequence length demodel, batch sequence length demodel as well, and then our output is batch sequence length, and then our target vocab size. Next step is our label. So we want to compare the output with our label, which is the ground truth of, if we pull up our HuggingFace, our label is our ground truth. So this translates to come on, this translates to not embedded. We have our model try to translate this to English, and we get to compare if this is actually true. So that's the label. Then we compute our loss function with the simple cross entropy. We're basically comparing the projection output. We're projecting it onto the target vocab size, looking at the labels, and we compare them together to find the distance between them, which is our loss, the amount of error that we have. And then we put that into our batch as the loss parameter. Let's first log the loss. And then we want to backpropagate the loss, which is this. Backpropagate. Zero out the gradients, and then update the model parameters based on the finished epoch that we have just had. And that is global step increased by 1. So we just completed 1 global step for all the batches in our epoch. Few more things left to do. We want to run the validation at the end of each epoch, see how we've done, see the progress of the accuracy of our model so far. So let's just run the validation. We'll write a function to do that. Validation, it takes in the model, the validation data loader, both tokenizers, sequence length, device. What else should it take in? Yeah, global step, writer. Yeah, so I think all of this hits it pretty well. Before we forget, let me put a reminder to myself to run the validation. And then we want to save the model at the end of each epoch into an actual file. So save model, checkpoint. So we store our epoch, the state of our model, state of our optimizer, and then the global step. We save all of that. The file name that we want to save to is get weights. We don't store the global step. And then torch.save. So we store our checkpoint and then store it into our model name. Now we run our validation. Basically, we just want to see how the model did. So model.eval, set our count to 0. We don't need total loss. And then we have our source text, expected and predicted. So expected and predicted. First, we want to get the console window width. So let me write a comment. Get console window with os.popen, steady size as console. we default to 80 with torch. No gradients. Make sure that nothing is affected. With our actual model, we're just validating to see how the model is doing. So nothing is affected here. Increment our count. We want to put our encoder and decoder mask again. Let's just make sure that batch size. That's great. And then the output for our model is we want to greedy decode. So source text, batch text. And then we want to compare all of these. Oh, that reminds me. We need the batch iterator to print. We need the batch iterator print. Lambda. Perfect. So now we use the print message that we get passed through. Now the batch iterator is printing it, not this function. Print message, we essentially want to print the source expected and predicted to console with. This is just making a horizontal line in the console. Great. So now we are basically making sure that text that we display doesn't go off the screen. We want to give it a buffer room of 8 characters-ish. You know what? We can do 12. Let's do 12. If there is a writer, then we log everything. We don't need another function to do this. So metric equals torch.metric.error rate, and then CER. Let me make sure to import torch metrics. We also want to compute the word error rate. So compute the word error rate. That seems right. And then we add both of these to the writer. We also want the blue metric. So metric blue score. So that is our whole validation process. We do need to still write the greedy decode. So let's do that. Def greedy decode. Let's make sure to specify the max. The reason why it's called greedy decode is because we want to decode the source sentence to the target sentence with our model by taking the most likely next token at each step. So let's first specify the start of sequence and end of sequence IDs in the target languages token. Then we do our encoder output. Then that peak. Then we want our decoder input. Okay, remember that this is just the same thing that we would have done in any encoder step. This is initializing the decoder input with the start of sentence token. Now we run this loop to keep predicting the next word with what our model knows. Let's first check that the decoder input is big enough. We build our decoder mask using the Causal Mask that we talked about last time. Causal Mask. And then we calculate the output. So output, we just decode it. And then now we want to get the next token. We want to project all the probabilities. Cool. Model.project. The next word is just the maximum of the probabilities. So this is the probabilities, but we don't need to know the probabilities. We only want the next word. Our decoder input, after we find the next word that we want to put in, we want to concatenate this next word into our original decoder input and then feed this input again into the decoder. We just keep looping. We concatenate the decoder input with a empty 1x1 tensor filled with the most likely next token with the same type as the source. The only way we break out of this loop is once we predict that the sentence has ended. In which case, if we predict that the next word is the end of sentence token, then we just break out and then return the decoder input, which should be our finished sentence that the model has predicted. We want to squeeze that because we added this extra dimension that we want to squeeze out. That's greedy decode, and that should be the completion of our model. Now, let's run it. Warnings. Filter warnings, ignore config. So now let's run our model. Wait, there are some little errors that I forgot to change. First, the tokenizers import is completely wrong. Word level and white space are not from tokenizers, but they're from tokenizers.models. From tokenizers.pre-tokenizers is where the word level and white space are. So that's that. All right, I did some debugging off the camera. Here are some final changes I made to the code before we are ready to train. So in the transformer class in our model, I forgot to put the encode, decode, and project functions, which we call in our training here. So I coded them up really quickly. The encode function takes in the source sequence and the source mask, then makes the embedding, and then adds the positional encoding to it, and makes the encoder from the source sequence and mask. The decoder is similar, takes in the encoder output, source mask, and then the target mask and sequence, and does the same process. And of course, we already know what the projection layer does. Then for our data set, most of you use Macs, and maybe you want to use a Mac to train your model. So in the bilingual data set, I made it so that each one of these tokens would also go to the device. So I would find the device here, and then the SOS, EOS, and padding token now all go to the device. In the get item, this is the same thing. I get the device, and then the encoder, decoder input, and then the label all have the device specified to them now. And then I also got rid of the torch.tensor in front of the SOS and EOS tokens because we already specify up here that these are torch tensors with that type torch into 64. So that's all good. And then for our Causal Mask, I also put it to our device as well. So everything will be on the device, so we can train it on either the GPU or if you're on Mac OS, the MPS. And then one final debugging change I made is I put config here in the function call of the build transform. But of course, if you can see in model.py, build transform does not take in the config. So I got rid of that. And then I also put our whole model into our device, so then the model can be trained on our device. And then I also made these lawn types, so then if you're training on this on Mac OS, the MPS won't interfere with the type that is on the device. Now to train our model, if you're on Windows, to use GPU, watch this YouTube video. If you're on Mac and you want to use the MPS, just install this. That will install everything that you need for the MPS to get everything running. PIP install all of these necessary libraries. Tokenizers, datasets, TQDM, torch metrics, all that kind of stuff. And then once you do that, we can literally start training once you do that by running the train.py code. I'm on Mac OS right now demonstrating you on the video, so I'm using the device MPS. And keep in mind that we are using this dataset, the AF to EN dataset. It made the tokenizer for them. So if you take a look at our tokenizer, we have our special tokens, and then we have lots of really interesting characters, and it's like a dictionary. So TE is mapped to 17. Oh, never mind. There is a bug. Let's fix that. One of these sentences is too long in the dataset. You'll see that the computer is lagging a little because it's actually training the model. So I will stop it here. But you see that now it's been training for very long and no errors now. Because one of these sentences, like this one in particular, it's a very long sentence. I changed how the get item works in the bilingual dataset to iterate through the whole dataset and just try to see if we can extract the data. And if the sentence is too long, we would just throw an exception and then move on to the next item. Two more fixes I realized after training my first Epoch on my GPU is batch size has to be 1 here because it's a validation loader. And then for our config, it was .format Epoch, but there was nothing to format. So I just put the format in the actual string. I ran into more errors through validation. So when we validate, of course, the dimensions will be a little messed up because the batch sizes are 1. So we want to normalize across the whole feature dimension, which means we need to change our layer normalization to take in the dimensions of the features, which is just D model, and then normalize it across D model, which means every time we see layer normalization, we're going to have to pass in features through the constructor. So here we want to turn off the bias for the weight matrices because we don't want to learn 2 parameters for the weight matrices. We just want to learn the weights. And here we pass in D model to the encoder and decoder as the feature set that we normalize over. So the features here. One last thing is I'm going to change the way I format the model file names. We are essentially adding the language source and language target to the model file name directly, attaching the epoch after instead of putting that in the config, which I feel like is a little easier and it's more intuitive. I just completed the first epoch for training the model. I switched to 2 different languages with a smaller dataset so that each epoch could go faster. As we see, the transformer after 1 epoch has barely learned how words fit together, especially since the dataset is so small. We switched to a different larger dataset and I coded up a notebook to help visualize the attention at work for the transformer. By the way, all the code is published on GitHub, which is why I felt that I didn't need to bore you guys through the process of coding the bonus visualization aspect. First, we import the necessary libraries and identify the device, do our necessary config and model declaration. Here we see that we are grabbing the 10th epoch for the model. Next, here's our function to fetch the next validation batch to be able to run our modified visualization. While we run the validation, we will track how the model is doing, especially visualizing the attention heads. To visualize the attention matrix, let's put it into a data frame. Then we extract all the attention scores from way back when we coded attention in model.py. Now it all comes back full circle. To visualize these scores, I'm using a Python library, Altair, to create the very nice chart that you will see soon. We call the function above, and let's watch the magic of the encoder. Green means 0 attention, blue means full attention. For now, we see that both the X and Y axis are the encoder input tokens, which makes sense since this is self-attention. As we watch the gallery of the greens and blues, try to notice patterns for yourself. For example, feel free to notice how each of the heads are watching a different part of the interaction of the sentence. The model pays close attention to the location of where the right and left parentheses are, which makes sense because words between the parentheses are read differently than the words in the normal sentence. It is learning to find the parentheses pairs. I'll leave you with one last thought. This is just the 10th epoch of training a model of around 4,000 rows, which is nothing in the world of big data and ML. So the transformer is far from perfect because I use data that isn't large for demonstration purposes. So you will see that it will pick up on some patterns, but largely it can't form really strong relationships between too many words yet. I encourage you to try out building a transformer yourself and feed it amazing data to see the results you may get. If you get any questions, especially questions about things to learn in ML generally, feel free to reach out on my socials. And with that, enjoy the attention visualization and happy coding.